Can you hear me now? Yeah. Oh, okay. So in the ADS and flat case, not only lack of time, also because I really don't understand very well anything about even classical observables in this ITER, which is the most important case, for us. And I will give some reference in this case, and some work done by Sandip and his collaborators, and by Suvrat and his collaborators. And I think there are many others when it comes to this, probably the most important case. But unfortunately, I will not cover this today. And I will look at d equal to 4. All the references I will give in the end, towards the end of the lectures. Okay, so roughly speaking, we can divide the class of classical observables in 2 categories. And as we go along, I will show you different nuances that occur for 2 categories. So one class of observables are what are called boundary observables. And the other one, which are far more counterintuitive in some sense, and probably more, quite rich, are what are called relational observables, or what are bulk observables. So let me first describe what these boundary observables are, which are actually formally very easy to motivate, because the point is that any observable in gravity has to be diffeomorphism invariant. Under all diffeomorphisms which do not change the boundary condition. So under all small diffeomorphisms. Just a small caveat for students, that there are 2 ways the small and large diffeomorphism is used in literature. One is where you have diffeomorphisms connected to identity, which are called small, and the one which change topology are called large. But for the purpose of this discussion, we will think of small as all the diffeomorphisms which go to identity at the boundary. So we will never look at topology changing diffeomorphisms, because we are looking at classical gravity right now. So we are going to avoid topology change. So by small diffeomorphisms, all the diffeomorphisms from whatever the manifold is to itself, such that phi on the boundary of the manifold is identity. Okay, this is the definition of small. And this is the same definition for both ADS case and the flat case. Things are again more subtle for this ITER, so we will avoid it, and maybe in the end we can have some small discussion about this ITER. Okay, and so then of course then it's clear that anything that you define intrinsically on the boundary is a gauge invariant observable, because it's not going to change under small diffeomorphism just by definition. And so you consider, let's say that your bulk fields, let me first start with ADS case, and let's say that all the bulk fields are the metric and any other field, which I collectively denote as phi. It could be any matter field, for example. And so now if you consider, let's say in Pfefferman-Graham gauge, you look at anything, all the fields that you obtain on the boundary, which includes all the boundary observables, will be generated by I should say this is ADS, right? So this is lambda less than 0. And then we will discuss the flat one. So all the bound generated by, for example, the stress tensor, and whatever are the normalizable modes of the matter fields on the boundary. So let's just denote them as phi. Okay, but this is just a set of observables. Right now we have not said anything about the algebra, even classical algebra of these observables. So, but clearly this is a set of all boundary observables in ADS. Ashok, you have a question?
Do you put any restriction on how fast it should fall off at the boundary, or
At this stage, no, it's just that we are looking at, for simplicity, Dirichlet boundary conditions. So I've fixed the boundary metric, but no, nothing. Right now in ADS, no, nothing else.
Okay.
Yeah. Sorry, I should maybe say that. If you do not, of course, if you do not put Dirichlet boundary conditions, then even the boundary metric is one of the boundary observables. But then we are not interested in that case, because then from ADS CFT perspective, even the CFT becomes gravitational. So we want to avoid fluctuating boundary conditions in ADS at least. So this is in the, yeah, thanks Ashok, with Dirichlet boundary conditions. But I don't want to dismiss other boundary conditions, because there is a lot of work which has gone into looking at mixed or Neumann boundary conditions. We can, again, if there are questions, we can, at least I can give you some references about those more relaxed boundary conditions. Oh, yeah. Normalizable mode, yes. So normalizability will stay, but if I relax the Dirichlet boundary condition to say Neumann boundary condition or fluctuating boundary condition, including normalizability is okay, then the boundary metric is also, which is right now just non-dynamical mode in the Dirichlet, it will become a, but then you know that this was, I think this work in ADS was pioneered by Marolf and his collaborator. It's called relaxing boundary conditions in ADS or something. But we will yeah, not this, yeah. What condition what we call the non-normalized? Yeah, exactly. And now the one interesting thing is that this is a set of observables, not an algebra at this point, even classically. And a point which is maybe for students a warning sign is that we don't really know in general what the algebra even classically of this boundary stress tensor is, in the following sense, that if I give you some example, that if I give you, let us even consider a fixed time slice on the boundary, let's just call it a sigma. So this is when I only draw, if I don't shade this, it's a Cauchy slice only on the boundary. And so let us consider, a point x and x prime on the boundary. And let's say that we want to understand, okay, can I even define some sort of a Poisson bracket between x and x prime in any classical theory of gravity with some matter, etc. Now, in general, if I don't smear this with killing fields, the isometries of the boundary, we don't know what this is, because this depends on the theory. So this bracket is not known in general, but of course we expect, and this is important, we expect it to close under boundary observable. We expect it to close in the set of all boundary observables. Of course, there are special cases. For example, if I smear this with isometries of the boundary metric, so if I define q zeta as integral zeta dot t, and this is some normal to the sigma, and then if I look at the bracket of, you can ask, okay, can I compute from first principle in classical theory? Can I at least compute this bracket for any two isometries? And if I don't want to use ADS CFT or look at the fact that this is a stress tensor in the CFT, just from the perspective of boundary, this itself is quite a nice but a complicated computation. And this computation indeed shows that at least when zeta and zeta prime are isometries of the boundary metric, it closes as we expect from the fact that these generate symmetries of the boundary metric. This was shown by, I think this is a very pretty paper. This was proved by Hollands, Ishibashi and Wald. But you also see that this derivation is complicated in the sense that if zeta was not an isometry, their procedure fails, because of course then it will depend on the theory, and Hollands, Ishibashi and Marolf. So I again want to just insist that we are not using the fact that this is a stress tensor of a boundary theory. I just am looking at classical theory where these are some complicated non-local observables from the perspective of the bulk. And all I have is a symplectic, I have a Poisson bracket of fields in the bulk. So that's the question we are trying to ask. I have the usual Poisson brackets of field in the bulk, and I want to use it to somehow compute these kind of brackets. And that's very, very complicated. No. Just boundary. Sigma, sorry, yeah. Now this, yeah, sorry, yeah. No. Sigma was, yeah, I should have, yeah, thank you, yeah. This is sigma, and if I do this, let me call it sigma bulk. Yeah. But the point is that if I just go from classical theory, I have some Poisson brackets on sigma bulk. And if I ask that, okay, what are the Poisson brackets of these quantities? That's very complicated. But what you can show is that using that Poisson bracket, you can indeed compute this. It's very nice analysis that they do, but we cannot do it. But we expect, of course, it to close among this set. So formally, there is an algebra, but the algebra, we don't really know even classically what this algebra is. So that's some small caveat that Raghu has a...
Yeah, I have a question. So you say that the Poisson bracket is known on sigma bulk.
Yeah.
So then don't you have to just restrict it to sigma?
No, because of the fact that Poisson bracket will just go to, because the fields are decaying, naively that will just go to 0 on the boundary.
Okay, then so that strip off some power of z and...
it's a bit harder because what you really want to do is the following. I'll tell you the procedure they do a little bit. You say that, okay, give me some Cauchy data, which is falling off. Now you evolve it and you get some solutions in classical theory. So if you could define Poisson bracket on the space of solutions, then you could use those to pull back you could use that to define this bracket. These are called Pius brackets, and so these are brackets on the space of solutions. So it is, I don't know of any procedure where on single time slice, if you give me bulk Poisson bracket, you could directly obtain, even by stripping off, as you are saying, this bracket directly from the bulk. Because usually what we would like to do is, if you had a symplectic structure on a slice like this, then you could push it forward and obtain a symplectic structure here. But we don't have it, right? We only have symplectic structure on Cauchy slices. So I don't know, I'm not maybe answering your question properly.
This Poisson bracket Tijx prime for all times?
Yeah, for any time slice, So I mean, sigma could be on any so for simplicity, yeah, you're right. So take any Cauchy slice on the boundary and I want this to be an equal time, let's say, bracket, only that, nothing more. But even to do this computation purely, these are only on a boundary. I don't know of any procedure where you could take a symplectic structure in the bulk with normalizable boundary conditions and obtain this bracket.
Sorry, I think I'm not being clear. So if you have sigma bulk, there's a boundary of sigma bulk.
Yes.
So on sigma bulk, you have some Cauchy data.
Yes.
On that particular boundary of sigma bulk, can you just get it by restriction or not?
No, you cannot get. No, because it is, because restriction is 0 of the symplectic structure on the boundary. Maybe we can, yeah. 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 Yes. That's all I'm saying. Yeah. But the way to do it is to really, yeah, I mean, okay, maybe we can chat about this. But the statement is that if you give me a Poisson bracket on the space of solutions, then you could somehow use it to derive the bracket. But even then, there is no, I mean, if you just look at their analysis, it is not known how to do it if you take zeta to be not an isometry. It's like very crucially uses the fact that given a bracket on the space of solutions, you can pull somehow, take that bracket and induce a bracket only on these charges where zetas are isometries. So maybe there is a better way to do it, but at least this is what is known so far as I understand. I don't know if that, yeah. No, this is more full classical theory, no problem. I mean, no, so that is the case, we are Dirichlet boundary condition. So isometries on the boundary metric are just Minkowski isometries, right? I mean, so
just the asymptotic isometries of the full space.
Yeah. But the theory inside can be just nonlinear theory of gravity coupled to any matter. It's not a problem. No isometry. Yeah, it's asymptotically ADS. I should have maybe said that.
I have this little confusion. We know the symplectic structure under Cauchy slice, right?
Yeah.
I mean, suppose I'm doing Hamiltonian method.
Exactly.
Okay, so I have a certain slice. I have the symplectic structure there. Then you are saying that that's not enough?
No, that is of course definitely not enough, because that's not even physical, because that is kinematical, that is not gauge invariant. So we have to quotient by gauge transformations.
No, I'm in a fixed gauge. Suppose I know how to fix the gauge.
Yeah.
Suppose I'm in ADS, I fix the maximal.
Yeah.
Gauge. I have the symplectic structure.
Yeah, okay. Then it's not enough, as far as I understand. It's not enough because of this fall off behavior. We don't know how to do this.
What is this follow? Can you just explain this a little bit?
So because the stress tensor is really falling off a z-square order, right, in the Pfefferman-Graham expansion.
Right. So
the symplectic structure behavior is such that you just naively try to compute this, you get 0. Because the
pi and phi are both 0, actually.
Everything is 0 at the boundary from that perspective, right? It's normalizable mode. So maybe as Raghu is saying, there may be a sophisticated way. I'm just saying what is known in the literature is that we don't know these brackets so far. Because the theory is not free, right? I mean, in general, the theory could be even from conformal field theory. We don't know the theory, right? So these brackets would depend on the dynamics of the theory. If you think of it from CFT perspective, also, right? There will be no universal answer to this, right? I don't know if that helps. This is like a 2-point function of stress tensor, right? At the end of the day, and that depends on the dynamics, right? So we would not expect a universal answer to this question in ADS, no? I don't know if that helps. That's at no. I mean, not late time. I'm just saying that we just take normalizable modes. No, yeah. Maybe we are related to what I'm saying. I'm just saying that we are looking at the fields which are normalizable. I just take Poisson brackets. I say, as Penta said, in a fixed Pfefferman gauge. I ask the question: can I compute this bracket from there? From the usual canonical analysis, I think you cannot. There is no direct way to compute this. In the same way that if I give you in flat space ADM formulation and ask, can you from there compute just the bracket on field, different, if you have some spatial infinity, can I compute the bracket between different fields at the end of spatial infinity from ADM bracket? We don't know how to do this. Because sorry, I couldn't hear the question. Can you say again? Was it a question or? Oh, I see. Okay. So okay, maybe let me go on. So what is the advantage and disadvantage? The advantage is that given any set of fields, like it could be massive, massless, anything, doesn't matter. In principle, we could look at all the boundary observables, which are boundary, like in the gravity case stress tensor and whatever all the normalizable modes of other fields are. And in principle, we could generate this kind of equal time brackets on any boundary Cauchy slice, for example. Okay, in principle, but of course, we from general perspective of CFT, we know that we will not get some answer which is theory independent, right? If we change the theory, then of course we expect this to change. Yeah. Is solution dependent? Certainly solution dependent. Yeah, thank you. Yes. Unlike the charge algebra. Thank you. Yeah, maybe that is a good way to say this. Yeah, exactly. It's that is why on the space of solutions, whatever is solution independent, that algebra we can define, which is the charges. So thanks. Yeah, exactly.
Please, can I clarify the figure? So there you drew sigma and sigma bulk at different times.
No, that was because Sandip. I got no.
So you just
a schematic.
Yeah,
no. That was sorry. Just because I initially drew here and then. Yeah. No. I apologize. Yeah.
So then, why do we need to talk about the space of solutions if all you are thinking about is just this one Cauchy slice which has some boundary?
Any Cauchy slice? Yeah, any Cauchy slice.
Why do we even need to talk about the space of solutions?
No, because as he said, right, that this bracket. Just think from the perspective also boundary theory, right? This is a 2-point function of the stress.
The bulk.
Yeah, so I'm just saying that argument that, we try to do it. I mean, if you try to do this from the Poisson bracket, there is no known way to do this because it just goes to 0. The bracket goes to 0. That's the first point.
Okay. Can I just ask this? That normally you define Tij as the variation of the action with respect to Gij.
Yeah.
Right? Response when you change the boundary.
That is this computation. So you use that to do this.
So is that the problem that to calculate the variation of the action with respect to Gij, you need to know the whole
you certainly need to know the whole solution. Yes, exactly.
I see.
Yeah. But maybe, okay, one more. Yeah. I can hear.
Confused because I thought that this bracket, we don't know it because we don't know what theory exactly is in the bulk. When
That's all I'm saying.
That's not dependent on the solution. It depends on the theory.
But also on the fact that it depends on the theory. Yeah, exactly. You're right. It depends on the theory. I agree with you. Yeah. Let me just.
Sorry, Alok. Sorry.
Yeah, go on, Suvrat.
Yeah, sorry, just to interrupt. I mean, this is some classical statement, right? So what is the point here? I mean, how it related to the, like, what is the point you're trying to emphasize here?
No, just the fact that when we talk about, because it's just for students, that we don't explicitly know this. The contrast will come from null infinity, where this algebra is universal.
Oh, okay, that's all you want to say, that in the boundary of ADS, the algebra is not free, and in null infinity, it's free.
Yeah, that was all I want.
Okay, that's all the point is.
Yeah. I was about to make that once I go to null infinity.
Okay, that point, I guess. Yeah. Okay, everyone. Yeah. Okay.
Yeah. No, I just, maybe I didn't know if students have, because we do see, as you know, Suvrat, that algebra of boundary observables, but I just wanted to say, even classically, this important difference is there about theory, universality of boundary algebra in flat and in ADS. That's all. Okay. No, nothing deep more than that. Yeah. So yeah. No, there's no follow-up.
Can you use the mic, please? Because I can't hear otherwise. Yeah.
No, follow-up subtlety is there's no follow-up subtlety. Follow-ups are follow-ups. So you cannot use naive equal time Poisson brackets to compute this. Marolf, Ishibashi, and Holland show that, as Ashok mentioned, that you have to realize that T is obtained by varying the action with respect to the metric, the source, and so then you use that to define some covariant Poisson brackets on the space of solutions. And you use that, they use it to show that at least when zeta is isometry of the boundary metric, you can compute this.
Lower equation is defined different from the T in the...
No, it's the same T, of course.
As in it's defined by varying with metric, but like...
No, it's the same T. It's just, this is smeared by zeta, this is not smeared by zeta. There's no difference. It's the same, it's a specific... When I say this, I mean, of course, we could, instead of looking at point, we could look at we could just do this, right? Any zeta dot t dot normal to zeta, where zeta is not an isometry, arbitrary vector. Then we don't know the bracket. But if zeta is an isometry, we can compute this bracket.
I thought you argued that by saying the follow-ups are such that it will just vanish. But like...
No, that was, that was from perspective of the fact that if you use ADM brackets, we don't know how to compute this. We don't even know how to compute this, as far as I know. But we know how to compute this using some brackets on space of solutions. But the method that they provide, that method, if you just study it, you will see that it will not generalize if zeta was not an isometry. That becomes immediate. And I have talked to Don also many times, and he says that it's not entirely clear to him if one could make up, one could generalize this if zeta was not an isometry. He has some idea.
There's a lot of discussion, but it's a really trivial point, right? If you make it in even the quantum theory, as students might know how to compute 3-point functions, that just 3-point functions of Tij are non-trivial in ADS, and they'll be trivial in null infinity. So
but as Raghu was, that was the argument I gave from CFT, but Raghu said he wanted to know from bulk perspective. So, but I'm not disagreeing. I'm not disagreeing. It's just
Hij on the boundary has some non-trivial 3-point function. So why do we have to even do the classical person? I mean, we can, but yeah.
Oh, why? Oh, okay. I thought I'm just starting from classical observable, Suvrat. So you are right. I'm agreeing with you, but we can see the same point you're making already at classical level, no? Or
okay. Yeah, I'm just saying,
I didn't want to belabor this point, but some questions came which I didn't anticipate. So sorry. Okay. Okay. Now let me. If this part is at least okay, that there is an algebra, although it's theory dependent. Let's go to the flat case where the contrast becomes a bit sharper. That is why I wanted to actually mention this point, but with another caveat that comes in. So I apologize, I'm spending too much time on classical theory, but just because of students, I thought maybe it's not a bad idea. So okay, if you go to flat space-time, and if I have any, let's say I have some metric and some, let's say some massless scalar field, and let's say some massive scalar field for simplicity. You could add other fields also. So let's say that we want to look at the same setup, and we want to look at boundary observables in a theory where gravity is coupled to say one massless scalar field and one massive scalar field. The action could be anything with interactions or anything. And now here the situation is slightly different, as you could imagine. So let me first, for a minute, forget about the massive scalar field. We want to look at massless scalar field. And here we know that how to define Poisson brackets, kinematical Poisson brackets on a Cauchy slice. So you could envisage that in this case things is a little better, because all the massless fields we know like decay in a power law behavior to null infinity, future or past null infinity. By the way, I'm not explaining what these boundaries are, but at least these ones are. So if there any question, please ask. Don't hesitate to ask. I'm just assuming people have seen this null infinity compactification of asymptotically flat spacetimes. And so now if here you could imagine that, okay, if I give you canonical brackets, I could like push this Cauchy slice forward in time. And of course, this Cauchy slice will then get deformed to scry. And because the symplectic structure is conserved in time, you can at least see that, given the Poisson brackets on this, I could how to get Poisson brackets on the boundary fields. So at least you can envisage why you could directly induce a bracket on scry from the bracket on, in the Hamiltonian formulation in the bulk. And of course, the subtlety, there are some subtleties which are which are technical. I mean, so because of this perspective, you can check that if there are following are the boundary observables for this theory. I'm just for simplicity taking one massless scalar, but you could take any massless field for this part. And all the boundary observables, if you only have massless fields, are observables on either scry plus, so let me call it A scry plus or A scry minus. And this A scry plus algebra is generated by in some sense, whatever is the radiation content of the metric. So that's typically called the shear. And I will explain the notations. So let's say the coordinates, let's say the affine parameter is u, and the angular coordinates on the null infinity are unit vector on the sphere. Then this is whatever is the radiative part of the metric, and A and B are the the components on the sphere. One is 2. And then whatever is the radiative, in some sense, radiative part in the scalar field, normalizable mode of the scalar field. So again, I'm insisting we are not in free theory or anything. It could be any generic theory of gravity coupled to scalars, and the boundary observables are generated by these modes, where C, just for completeness, C satisfies, C is symmetric and traceless. So C has only C is. So again, like in ADS case, let us fix the boundary metric on the sphere as a non-dynamical metric. Let's call it Q. And this is similar to ADS where we are not wanting to change the boundary metric. Then C, one can show that C simply satisfies QAB, CAB is 0. And that, so it's a symmetric traceless tensor on a sphere. So it's like, two modes of the graviton, which makes sense because this really only measures the gravitational radiation that leaks out. Yeah.
Sorry, what about the fields on scry plus minus? Why are they not part of the algebra?
No, not yet. I was about to come to that. So right now, yeah, that's an excellent point, and I will just add it now. I mean, this is that's a very good point. So to begin with, this is an algebra which is algebra in. So scry plus really is minus infinity to infinity. And as she's saying clearly that this algebra clearly excludes modes which could be sitting on equal to minus infinity sphere or equal to plus infinity sphere, and I would just add them in a minute. So so this is really an algebra without the scry plus minus, which is boundary of scry plus. And one can show that because of this argument I just gave about the Poisson bracket, one can immediately show that for any theory, one has universal algebra generated by these fields. So if you take C and then one can check that and similarly.
Suvrat, these also fall off, right? At infinity.
Yeah, this also fall off at infinity, exactly.
Yeah, so what is the difference from ADS? I mean, what?
No, there is no difference. Really, to compute this, you also have to do space of solutions analysis, but I gave an intuitive argument as to why we envisage this to come out nicely. But the difference is simply that you can check that they are theory independent. It's the same analysis you could do, because these are becoming free fields at infinity, null infinity, unlike in ADS case, the brackets have become universal.
So what is the intuitive argument? Maybe I didn't get.
No, intuitive argument simply was that null infinity for massless fields is also Cauchy slice.
Okay.
So that was the intuitive argument. So then, because symplectic structure is conserved on a Cauchy slice, so we can at least zeroth order imagine why we would be able to do this.
Okay.
Any bulk theory, you could have any interactions in the bulk. Of course, I'm assuming we don't have non-local interactions, only local interactions in the bulk. And so that's, again, this is, okay, so here there is a nice advantage in some sense compared to ADS.
This was true also in ADS, no? Because you are trying to calculate the Poisson bracket on a Cauchy slice of ADS.
Yes.
So,
but the boundary Cauchy slice is not obtained by deforming the bulk Cauchy slice. So there is no natural conservation of simplex, right? But really, Ashok, what you are saying is absolutely correct. I can follow the same procedure Ishibashi, Marolf, and Holland follow, and do the same thing. And I just follow the procedure and don't assume zeta is any symmetry of my null infinity. Then their analysis produces for me these brackets, whereas in ADS it will fail. So one could also check it just at that level. Okay, but of course, so this is a very nice thing about flat space, because the fields become free at null infinity, massless fields become free no matter what the interactions. We have these universal theory independent brackets which generate this boundary algebra, which is not complete. It is only algebra on scribe plus. But slight price we pay is that if you had massive fields, then this will not work. So if you had massive fields, so if we add now in our bulk field spectrum, if we also had including some, let's say one scalar field with mass m, then it is one could study the solution to equations of motion of this field and immediately check that it decays faster than any polynomial at scri. So these fields have no hope of, they just don't reach scri in some sense. They only reach what is called time-like infinity if you go to the future. So all the just to quantify it a little bit. So if I take this field, then its fall off as you go towards scri, let's say scri plus, is goes like this. But if you take psi with a mass m, and if you do this procedure, then you can just see that by looking at equations of motion, even free field equations of motion for psi, you can show that this goes as it falls faster than any power law in R, and so that means these fields, we have no hope of detecting these fields at scri. They just don't reach scri. But what they do is, if you instead of going to scri, if you take time to infinity at fixed R and you go to I plus, what is called I plus, then again I'm being a little schematic. Then you can show that these fields go as just exponential decay, faster than any polynomial. Yeah, maybe I should it will be minus m. Some r to the alpha. Now this so okay. So it's a nice thing to check that it's nice that if so that means we have to include in our boundary, if you want to define all boundary observables, not only this scri plus but also the boundary of scri plus, which is this one. And so to define full boundary observable algebra, we have to look at scri plus. So the full boundary observable algebra is defined on scri plus union I plus. But I plus is really, if you think about it, u equal to plus infinity. If you use the affine parameter on scri, which means that I could just relabel it as scri plus plus. So that means that maybe I should put it like this right now. So the boundary algebra, if we had massive and massless fields, the boundary observables would necessarily have to include at least one boundary of scri. But if you include one boundary of scri, you can ask, okay, can we have observables which are non-trivial on the other boundaries of scri? So in principle, could we have any fields which are non-trivial at u equal to minus infinity? Certainly these cannot be massive fields, because massive fields are not reaching anywhere near scri. But if you have static modes in the massless field, so if, for example, if you consider if you consider this field C, and in this C, if you had a mode which is static, so if your C, so please ask if I'm saying some, and there are many experts in this here, bigger experts than me, so they will correct me also. If you take, say, u going to minus infinity, and this is what generically will happen if you study radiation. So if you take u going to minus infinity and you get a mode which is, let's say, CAB0 x hat, like this, that means that you must include modes also at scribe plus minus or equal to minus infinity. And so now that implies that our full algebra of boundary observables will be the massless fields at scribe plus, which have finite energy, and the massive fields at I plus, which is scribe plus plus, and static modes at scribe plus, which will sit as fields on a sphere at scribe plus minus. Okay, and this is a free field algebra. This is a free field algebra because all the interactions are dying down, except in d equal to 4, we have infrared issues, which I will come to in a minute. And these infrared issues are not just quantum, also in classical theory, because we have long range interactions. So if I just for a minute ignore the infrared effects, I have a free field algebra for all fields for any theory of gravity coupled to matter, and that's defined on the full, in some sense, on the full scribe, which includes both the boundaries of scribe. So is this point okay? That's a very good point. So you would not be able to define all fields. I just give an example, but you would not be able to define all the static modes induced only by looking at u equal to plus infinity. You need both. You need both. Yeah, I think I'm just being a bit brief because we can't just because of lack of time. But so up to this point, is it clear that if I include if I exclude the infrared effects, then I have a universal algebra, which is a free field algebra, which is defined on a full scribe. Of course, everything I'm saying is in the one boundary, but because if I just do compactification in retarded coordinates, I only get one conformal boundary. But if you did in advanced coordinates, you get another coordinate boundary. So I should not have really touched them. They are just kind of independent boundaries. So you could define an isomorphic algebra at scribe minus also. So a boundary, which I have defined here, we could call it a boundary plus, but that would be, we could also equally well define it on scribe minus. Okay, and now I just briefly mention what these infrared issues are, because we'll not be able to go into them too much. And that can be seen by simply looking at minimally coupled scalar to gravity and studying the solutions to equations of motion. So we could just study Klein-Gordon equation for scalar field coupled to linear gravity, and we see that there are already subtleties in defining the boundary observables at I plus. So I will avoid saying too much about it, except the fact that the last equation I wrote gets modified. This is no longer true in 4 dimensions if you have fields coupled to massless fields like gravity. So this equation, let me call it star. So star gets modified by infrared effects. So I will just write the star goes to the equation that so you see that if I now expand this, the first term is actually the dominant mode at large t is log t by t to the 3/2, which is simply the statement, very well known statement in 4 dimensions, that asymptotically fields are not free. And you see that, of course, also in classical theory. And so if we have to rigorously take into account all the infrared effects and define the boundary observables at I plus also, we have to really look at this kind of dressed operate observables, where dressing is by this linearized metric at time like infinity. It's just a subtlety I want to mention for students because it's of course becomes important if you seriously study this algebra in 4 dimensions. Okay, with that caveat, I will end this discussion of boundary observables unless there's a question. Okay. Okay, so now we can define, quickly look at, I will be very brief in, from boundary observable, it seems like we only have very delocalized observables in the theory, which are only living on the either a single boundary of ADS or compactified boundary on flat, which is scribe plus including both the boundary points. But in classical gravity at least, there are local, I will quantify this a little bit more, local observables which can be defined as follows, which are called relational observables.
Yeah, Alok, you didn't introduce the Bondi mass yet, right? Or the ADM Hamiltonian, like that will somehow be important in your, what you say? Or?
Yeah, very important. Sorry, you are right. So one, another mode that which was related to your question, another important field that I forgot was of course the ADM energy, which is the mass at, which is usually we define it at spatial infinity. But from this perspective, of course, spatial infinity is u going to minus infinity. And so we could define, we would define in the full algebra. So let me write the full, thanks for it. So let me write the full algebra here. Let me erase some part and just rewrite the algebra at scribe plus at least. Maybe I write it here. So the algebra at scribe plus union scribe plus minus, let me forget the massive fields for a minute, will be the algebra at scribe plus along with the ADM energy density at scribe plus minus, which is, and this static mode that we wrote down. There could be many other modes, which I'm just not writing down. These are not exhaustive modes at scribe plus minus. It depends on, it depends on what kind of low frequency radiation comes out, and people are still struggling to parameterize all of these modes which survive at scribe plus minus. There are conjectures that these modes never terminate, and they give rise to what is called a W infinity algebra, but we will avoid all that discussion. So for our discussion, it is important to just appreciate the fact that we have this ADM energy density at each point on the sphere and the constant shear mode, which survives.
Is it really clear that the spatial infinity is scribe plus minus? Because I thought.
Yeah. No. That's a hard. That's a very good point. So there is no canonical definition of spatial infinity because of the fact that there are different compactifications one could do. And that's one problem with spatial infinity. So you could do this old Penrose compactification where this becomes a point, but that's very ill-defined to do any physics because then the scribe plus, which was a cylinder, kind of crunches. But there are other compactification where it is blown up to a hyperboloid or an Einstein cylinder, and there scribe plus minus is one of the boundaries of this blown up spatial infinity.
Okay.
So I think that's an interesting subject in its own right. Okay. And that's a good point. That's another distinction from ADS where even the scribe plus is like a universal boundary of flat space. So it doesn't matter what compactification scheme you choose, you will always get scribe plus. The spatial infinity is very much representation dependent, and different compactification give you different structures of spatial infinity. And they are really different structures, like you get a point or you get a hyperboloid, and they are not related by smooth diffeomorphisms at all. So that's another caveat that I wanted to avoid. So for us, that's why because the universal part of spatial infinity, if you want, is only the u equal to minus infinity sphere. And so that's the only one I'm keeping right now, which is the only one we will need for this discussion. I mean, there is a lot of work by Suvrat and his collaborators here in ICTS to look at fields at spatial infinity, but I think we will not have time, unfortunately, to discuss that. So let me go to relational observables very fast because I'm running out of time. So the idea of relational observables is quite simple, but they are quite interesting in classical theory. The idea is the following: that suppose you are given, let's say we have a simple example of, say, metric and four scalar fields. Let's call them phi I. And this I goes from 1 to 4. And now let's consider the following following observable. Let me just call it G. Or actually, let me add another scalar just for simplicity. Let's say that I look at let's say I look at another scalar field, let's say psi. Okay. So of course none of these are diffeomorphism invariant. They are local fields. They change under diffeomorphisms. But so consider the following functional, which is defined as where f is any smooth local function on of phi, functional of phi. So one good example maybe to keep in mind for f would be f is delta function. I mean this is too singular, but we have to smoothen it. But just for a so of course we can check that this, so this is a very complicated functional of G, phi and f and psi. But one can check that this is, one can immediately see this is diffeomorphism invariant because we are integrating a scalar density over the entire space-time. And so it's a trivially diffeomorphism invariant quantity. It looks very much delocalized, of course, because of the fact that we have integrated over the whole space-time. So how in what sense it is, in what sense is it buying us anything? But where it buys us is that suppose you look at f, which has compact or support, or let's say for extreme case, let's look at the delta function support. And so then this is telling us that we are evaluating psi. What is this observable then telling us? We are evaluating psi at a point x, at a single point x, at which fields phi I take value 4 numbers, phi I 0, they are just 4 numbers. So this is the point. So you see that we have got a local observable now because we have evaluated a field at a given point, but the point itself is fixed by the values of 4 other fields. So that means as long as
assuming there's some classical background that exists.
No, I was about to come to that. Right now it's just general statement of the older definition. Don't know nothing. I've not assumed anything, but I'll come to what you are saying now. This is only true if the map between x mu to phi I is invertible, which means these fields have to be sufficiently dynamical that they kind of chart out a coordinate system in flat space-time. So if you take some very homogeneous fields, then they will not give you a good coordinate system because they will not change under time, for example, right? So Suvrat, is that okay?
Yeah, I mean that's fine. Yeah.
Yeah. Okay. So this is of course a strong assumption, and one could argue that this, of course, one could say that this will never be true, because no matter what, the geodesics always coalesce. So at some point, our coordinate system, which is spanned by some physical fields, will always die down. Because if for example, just to give an intuitive argument, if you say that I have some particles and their world lines are going to chart out a physical coordinate system for me, and then eventually, no matter how far spaced or low energy these particles are, eventually the geodesics may meet and coordinate system will break down. Which is just telling us that this is not, there is no good global gauge fixing in gravity, but okay, for practical purposes, for large enough regions of space-time, we could envisage defining things like this. I will in a very quickly tell you a concrete model of this observable, which is called a dust model. But is there any question about this, why they are local? Yeah.
Better than using just x mu in themselves?
They are not diffeomorphism invariant. Psi is not diffeomorphism. Psi of x is not diffeomorphism invariant. It will change under diffeomorphism.
I'm getting confused because like phi is some dynamical field, right?
Right, but this is of course diffeomorphism invariant trivially because it's the integral of a scalar density, so it doesn't change under diffeomorphism. But
changes under
everything, all the fields change under diffeomorphism, because of which this does not change under diffeomorphism. If you take any dynamical field and you make a scalar density out of it and integrate, then it is diffeomorphism invariant trivially. That is not a big problem, the big deal. I mean, that's just trivially true. The point is, why is it local? In what sense local? And it's local because we have chosen 4 physical fields to give us a coordinate system. So if this is true, then we get a local field, right? Because we are saying we are measuring psi at a point x at which 4 phi's take specific values. This relation is diffeomorphism invariant. Like phi's change and psi change, but this relation between them don't change.
Anchoring to the boundary or anything like
No,
that?
I'm not. If I anchor boundary, it won't be local.
Okay.
Yeah. I mean, the point is to not anchor it to boundary. Otherwise, I wouldn't be talking. Otherwise, we already have all the boundary observables, no? Yeah.
Actually, somehow, I had a similar question about anchoring on the, on the boundary, which is sometimes in the context of ADS, we say we will shoot a geodesic from some point in the boundary and wait for some proper time or affine time, whatever, to locate a point in the bulk.
Yeah.
And we could define bulk.
That's a very good question. There is a beautiful paper that I will refer in the end by Philippe and his collaborators, where they show that how we could anchor this physical coordinate system to some boundary, and there's a very precise relation between these relational observables and the boundary observables. But if we do it like that, we get a kind of a picture that they are not local because we are anchoring them to boundary. So those are special type of relational observables where we are anchoring the coordinate system to the boundary. In general, relational observables are more general. So they include the ones you said. But these are more general because I don't have to anchor this coordinate system to the boundary, but it's defined by the bulk field itself. Okay, and there's a very concrete analysis of this relation by Philippe and his collaborators. So but
Alok, this is actually deceptive, right? Because of what you said. So in fact, in the end, presumably you're going to say that everything is anchored to the boundary. So these things look like they're local to in perturbation theory. But eventually we know that these are also going to go back to the boundary. So this is just some, I mean, it's kind of deceptive, right? That you
I'll just come to that, Suvrat, and I'm not disagreeing with you. Classically, of course, we have models, which I was about to come to in a minute, where they are good bulk observables and not anchored to the boundary, but they are only classical. As soon as we switch on quantum fluctuations, we lose control on these observables.
No, but it's not just lose control. You know that they won't be local, right? You can prove that they won't be local. So it's not just a question of...
we can prove that. Yeah, you are right. You are right. I was saying that we actually cannot even define them because they are, as you can imagine, they are composite operators. And so even at one loop, we don't, we lose all control, even at a more superficial level of how to renormalize them, etc. But I'm just saying,
So like these things that by Witten, Chandrasekhar, Pennington, and Kyriakos and so on that Tom was mentioning yesterday, these are kind of some versions of these observables, but they work in perturbation theory, which makes sense that they're local in perturbation theory. Yeah. But we shouldn't take them too seriously because otherwise they would lead us to believe that all like gravity is like quantum field theory, which we know it isn't.
No. I'm not disagreeing. I'm just saying that classically there are these observables we can define which are not local in quantum field when we switch on quantum fluctuations. Maybe let me just finish this classical discussion. Then, is that fine, Suvrat, or no?
No. Yeah, I agree. Yeah, sure, good. Yeah, classically it's true. Yeah.
I will give all the references, especially Philippe's reference, where you can find all the older references. History of relational observable is littered with martyrs who try to make them more rigorous, and it started from Bergman and Komar and it has gone all the way now. But I feel that the state of the art is this paper by Philippe, and I will write all the reference in the end. Yeah. Okay, but just before what Suvrat is saying, let me just at least say something about in what other way we can check that these are local, because I give an intuitive argument why these are local, because we are basically charting out coordinate system using some physical fields. But one could classically give a more precise definition of microcausality classically of these observables, and that is as follows. So one can check classically, and this is a result one can prove, and this was proved long back by DeWitt, and then it has been brought again into sort of mainstream by Marolf in series of papers, and the statement is the following: that if you take two functions phi, take two functions f and g, which have compact support, this is extremely important, I'm assuming this is true, then one can check that these are of course space-time fields, so we can't do canonical ADM brackets or anything, But one can check that there are these covariant brackets. Because I've run out of time, I won't be able to explain them, but if you want, we can discuss them later. And I think there are people who are real experts in these things. They are called covariant brackets, which are called Peyer's brackets, which are brackets on the space of solutions. And David showed, and later it was revived by Maros. And the derivation of this is also given in Philip's paper very nicely, that if you take psi bar of G, psi bar of F, and psi bar of G, and you evaluate it on some solution. So let me call it F prime, sorry. And these are brackets which you evaluate on a solution. So you take this, you evaluate it on some solution. And if with respect to this solution, F and F prime support is space-like separated, then this is 0. If support of F is space-like separated from support of F prime with respect to G0, the metric G0. And one can really make this quite precise in classical theory and check that this is true. So this is just quantifying our intuitive notion of locality of these observables, that they satisfy microcausality classically, or what was in older days known as Bogoliubov causality in quantum theory. Okay, so now is there any question about this? So another issue is that we don't know what their algebra is. It could be very complicated, but we could imagine generating some algebra out of these relational observables, because if you take these brackets of any two relational observables, it will be diffeomorphism invariant because they are both diffeomorphism invariant. They will generate a diffeomorphism invariant algebra of some complicated functions. Assuming we could find fields and they satisfy this invertibility everywhere in space-time, which is never going to be true, but we could say that okay, they should satisfy in some local regions of space-time at least. Ashok has a question.
The dust model is a special case of this?
Yeah, I was about to write just a model. As you know, the Brown-Kukash model is the one that is a very concrete manifestation of this idea. So one can worry that these things are very formal, and can we actually at least find some theory where these relational observables can be written down explicitly. Now we have a few theories like this, but the first one that I know of is this beautiful model of Brown and Kukash. So I will just give a reference because I've really run out of time, but the one concrete implementation of defining relational observables was in this theory called Brown-Kukash dust model, whose action was basically given by action of Einstein-Hilbert plus I will explain what the fields are. These are some different fields which are related to dust, degrees of freedom of dust. Where this u mu is a velocity field of the dust, which can be written as dou mu of some scalar plus.
Sorry, but Alok, this is all deceptive, right? These are all like physically somehow like wrong. Like this is some classical, taking the classical u mu too seriously and not trying to.
But Suvrat, I mean, isn't it true that this in perturbation theory, if it recurs to
in perturbation theory,
CFT with Kyriakos and all are shown, at least in perturbation theory, they give
in perturbation theory, it's true, but it's missing like of course it's true in perturbation theory, but it's eventually kind of wrong, right?
No, I'm on page. Are you saying we should not look at them, or?
No, we can look at them, but then we get to all these paradoxes if we take them too seriously. Like, if we by taking these kinds of things too seriously, then people say, you get to paradoxes.
We should not take them. This is an important point. So this is all classical, Suvrat. So we should not take them seriously in quantum theory. But it is true that classically people do define, and as you know, people do say that we can localize information based on these. So,
but are you saying that there is a no-go theorem in quantum theory that you cannot?
Yeah, I think that even in ADS-CFT, exactly. I think inspired by this, so these are very hard to define. But if you have recourse to CFT, we can define analog of these observables in ADS using CFT, and there is a no-go theorem that they will never commute with the boundary Hamiltonian non-perturbatively. So it has been shown.
Flat space time.
No, so flat space, we don't know rigorous proof, but we have with Suvrat, we have a proof which it will indicate this clearly, that we have this, which I will explain, that the boundary observables, no matter what states this thing create, even if they could create some states, there will always be boundary observables which will separate, which will be able to classify two states created by this relational observable. So I think there is a no-go theorem in quantum theory, which is what Suvrat is indicating. But there is a lot of claims and counterclaims in literature that this actually give us some localization. So even if you want to approach those papers critically, it's good to maybe know what these things are, because these are, except in Philip's papers and older papers, they are often not defined carefully. I mean, people just say some words and write something, but
Alok, I know you've a little time, but when in this exchange with Suvrat, you folks are saying this is okay in perturbation theory, but not beyond.
This is okay in perturbation. I will give the result. In ADS, you could use, in flat space, we don't really know, let's forget about holography. In flat space, order and perturbation theory, we don't even know how to define them properly because of the non-normalized speed of gravity. You can imagine, right? This is a very composite operator. And you have the square root of minus g and things sitting here. And then, you could, depending on what gauge you choose, you could get all sorts of non-locality when you actually try to renormalize this. So we don't know how to define this in a bulk theory, even if at one loop or higher loops, even at finite loop, we don't know. So these are formal in quantum theory. But if you do ADS, in ADS, there was this beautiful paper by Kyriakos and collaborators last year that you could use the CFT states to rigorously define this type of observables, where the coordinate system is actually defined by a bulk heavy state. Like you have a time dependent state in ADS, that is enough to give you an operator in CFT, which is relational in this sense. And what they showed was exactly what Suvrat is saying, that even for those operators, even in perturbation theory, these are local. Like if you look at the commutator of these operators with a boundary Hamiltonian, it is not zero non-perturbatively. There are this order e to the minus 1 by g effects which are never going to vanish. And so it kind of is a no-go theorem that Suvrat is indicating, which in ADS has been very precisely shown. That they will not be local. So that's why Suvrat is saying we are kind of wasting time looking at these things, but I mean, he's correct, of course, but I think that they are, in the history of GR, they are observables that people have considered and tried to work with. So,
So it feels like to define a state, you have to give like this phi 0i everywhere in space-time, right? To define the state in which you are calculating this.
Say the last line again.
To define these things, you have to give phi 0i, which is
phi
like
0i. What is phi 0i? Okay. So that's you're talking about this Kyriakos construction now.
I don't know. I'm just asking. Like,
So that is inspired by this notion, but it is a thing defined in CFT, such that the point is that if you take a state in CFT, which corresponds to a very time-dependent geometry in ADS, then you can use that state to define some CFT operators which are analogous of relational observables.
No. What I mean is like
we don't know how to quantize these in ADS. We don't know.
No, I'm just trying to ask, like, to define the state, you have to give phi 0i like in a volume worth of phi 0i, right? Like to define every point.
Dynamical fields. I mean, these are fields, no? We quantize.
No, the phi 0i is the background, right?
Phi 0 is some number.
Some number. So for every state, you have to assign volume worth of numbers. Isn't that too many numbers to define a state or something?
No. You give me 4 numbers, and I give you a state. I give you an operator which is localized at points determined by these numbers. I didn't understand what you are saying. If you want to quantize this, it's not a function of x. It's numbers.
These are numbers which map you to space-time points, I thought.
Yeah. So we are defining a diffeomorphism local field at a point in space-time. So we need 4 numbers. We don't need like infinitely many numbers. I want to locate a diffeomorphism operator at origin. So I need 4 numbers to fix the origin. I don't need infinitely many numbers.
Oh, sorry. I thought there's a one phi 0i map to every space-time point or something.
Right. So I mean, if I want to, that's true for any field. No, if I want to determine a field, I need infinitely many numbers. I mean, state.
Phi 0i is defining the.
No. Phi 0 is not defining any state. It's just giving me it is just telling me that if I wanted to localize the operator at a given point, I will need 4 numbers. I want to define an operator which is diffeomorphism invariant located at the origin. I want to find what that origin is. I'm going to define that origin by means of some operators. Yeah. Okay, so I just finished this, and then I think Suvrat will be mad at me for wasting time. But let me just finish this anyway. So you can check that with this action, you can show that so let me just explain the M is like the energy of the dust. T is like one scalar field of the dust, which plays the role of, is conjugate to the energy, and it kind of plays the role of time. So this T field of the dust kind of charts out the time coordinate, physical time coordinate. The Z's chart out the spatial coordinates, and W's are like conjugate to Z. They are like speeds of the dust. So this Z and T give us like a classically physical coordinate system. But there is no gauge fixing here. This is dynamically picked. So it's everything is gauge invariant, and these are some velocities of the spatial moment of the dust. And M is the energy of the dust. And Brown and Kukash showed that you can really use in this model, if you compute, you can use the Z and the T as the 4 fields to write relational observables in the theory. And they did a very quantitative and a solid analysis, which is again also reviewed in Philip's recent paper. So at least classically we have a model. Of course, as Suvrat is saying, it's deceptive because none of this works in quantum field theory, but at least classically there is this model that people use to define a physical coordinate system. Okay, so now I will switch to quantum theory in remaining 10-15 minutes. Any questions about classical observables? So all observables have their pros and cons. I hope that's the takeaway point that I can give you. That Raghu, yeah. Have they been useful in any? That's an excellent question. So that's a very good question. So if you of course in cosmology, when people do cosmology, for example, so if you want to do gauge invariant perturbation theory in cosmology, then these relational observables have been useful as far as I understand. People do use it. Because there's always this issue in cosmological perturbation theory that which modes are physical and not, right? And you could just do everything unambiguously in this way. I don't have a single case where you did something using this that you could not have gotten otherwise. I think that's your question. Sorry, I don't know any. But inflecton is like a relational clock. It's a very simple. I agree. But I would say that's a relational clock, no? So maybe Sandip answered it. Inflationary perturbation theory, practical use of. I think Ashok has found some use of Brown-Kukash model in string theory, no, Ashok, or later? No, I think Raghu's question is excellent. But I mean that one could Raghu say also about in general observable questions in gravity, right? Like usually we fix coordinate system and do our computations, right? So unless we ask questions. Absolutely. So except boundary observables, which are true generally, I think these because boundary observables at least in similarly flat spacetimes are just free fields, to all orders in perturbation theory. So those are really universal. So except those, everything else is which is also I think why Suvrat is saying these are a bit deceptive. I mean they're also, I would say, more than what's worth. Like they're deceptive also at a very basic level. I have never seen a single computation where this has been quantized at one loop for any theory. So in that sense, it remains formal.
So when you said that in ADS, these work in perturbation theory, but not non-perturbatively.
Yeah.
I mean, it's non-perturbative in which constant is it?
N.
I mean, if I take n to infinity limit, I mean the standard flat space limit.
Yeah.
Starting from ADS.
Yeah.
Then are there still these corrections or they go away?
Yeah, this I think Suvrat should be able to answer. We would expect corrections. I am 100% sure, but I don't know immediately how to do it from the ADS.
The state also has energy n squared, Ashok.
Yes, so that's background state.
This background state has to have, so it's actually non-perturbative in energy of the background state ng Newton. So if you take n to infinity, the state will also become infinity.
You need some infinite massive state.
Yeah, that's right, exactly. So n is only because, I mean, you could make it less than n. It just have to make the state, it depends on the entropy of the state actually. So they're actually non-perturbative in entropy of the state, density of states around the state.
Okay.
But yeah,
go on, Suvrat,
No, nothing. I mean, this is like saying that if we make things complicated enough, then of course we'll make it hard for us to see holography. Like gravity is not holographic if the background is complicated enough. That's why we don't see holography all around us. So either you should make the background simple or you should do very precise things to see the holographic localization gravity. But maybe, yeah.
Okay. That's a good, yeah. You are right. But even with complicated stuff, we will never really strictly see localize. It will not be localized, right? I mean, non-perturbative effects will spoil localization anyway, right? Is that correct?
Yeah, I agree.
Yeah,
I agree.
Yeah. Okay. So now I go to. So now let's focus on exactly as Raghu said. Let's at least start with the observables which we have control on, which are boundary observables. So I'm going to now, to begin with, focus on flat space. So say semi-classical or quantum even, semi-classical / quantum gravity in asymptotically flat space. And we could go to some orders in perturbation theory, or we could formally even look at just some say canonical quantization of gravity coupled to some scalars, etc. So what I'm about to discuss is equally true for both the scenarios. And here is let's start with our algebra again. So just for simplicity in semi-classical theory, let us only look at, because we really know how to make the statements precise only for massless fields. So let's look at the algebra only A scribe plus union A scribe plus minus as a boundary algebra. So I don't have massive fields in my theory, no massive fields. And we want to see whether we can, are these, in what sense are these observables enough to classify states in the bulk? And we will see that actually we don't need all of this, we need a much smaller algebra of observables. So no massive state.
Is made of massive fields, right?
We don't have now, we forget dust and all.
But I'm saying that then how, this argument then will not rule out this dust-based
no, it will rule out. If you just give me a minute, it will, because what it will rule out is that you give me any states. So I am defining my algebra of observables only at scribe, but in principle the states in the bulk could be created by something else also.
Okay.
The goal will be to see whether we can classify states which are localized in the bulk using only algebras and scribe.
So when you said that you assume there are no massive fields.
Yeah.
You are saying there are no massive fields at scribe plus, or no massive fields in the.
No, right now I'm just no. Right now I don't, because the analysis we do, which is the concrete analysis we do, we don't at this point, except the recent work of Suvrat and his collaborators, don't know how to immediately generalize it if you also include the massive fields. Partly because also infrared issues in 4 dimensions.
Okay.
And so right now let me just focus on this point. You will see that we will only. Right now, I really only have massless observables, like at scribe. Yeah, gauge invert observables created only out of, so no massive gauge invert, no massive boundary observables. Okay, so let me just recall what this what is the algebra is formally. It's generated by following fields. Then this ADM mass density, or what is called Bondi mass aspect at u equal to minus infinity. Then you can have some static modes at scribe minus, which I will call just indicate like this. Then you can have matter fields, which we collectively denote like this. And then we can have some complicated things generated out of polynomials generated out of all these elements. So that's rough. That's the schematically that's the algebra that we are looking at. And the remarkable thing again about this algebra is that this is precisely an algebra. Like we know what the commutators between any of these elements are, unlike in the EDS case. So it's not a formal algebra. At any order in perturbation theory, we know exactly the commutators because they are never affected by they are purely infrared and they are never affected by anything in the UV. Okay. Now, of course, you can say that. Okay. So now the question we want to ask is the following: that given. So let me first ask a dumb question whose answer is trivial, and then we will see the more very sophisticated question. Given two states, psi 1, let's say, and psi 2 in the Hilbert space of the theory, can I distinguish? Can I always find some element in this algebra such that for some A in A boundary, A. And this answer is obviously yes, because of the following reason. For this, we don't even need gravity. So let's consider a simple case of, let's look at massless scalar field in flat space-time. And let's look at the simplest example of free massless scalar field in flat space-time. And it has been known since a long time as a ironically precursor to HKLL that we can always write a massless scalar field in the bulk at any point in the bulk in terms of fields on scry as follows. I will explain the notation. This is capital phi and this is small phi, where x mu point is r u x hat. So just from the analysis of the Klein coordinate equation, we can show this is exactly like HKLL that we do, right? You give me some boundary fields, which are fields at scry, free fields at scry, and I can use them to define. So any bulk operator, at least in the free field theory, can be written in terms of the smeared boundary operator, where this smearing is only over the sphere at scry plus. So the bulk point is some localized at r, u, and the angle on a sphere. And this is just a inner product between x and, I should put 1 by, sorry, yeah, r here, sorry, 1 by r. This is some null vector which is localized at the point 1 q hat on the sphere, and there is some power I'm forgetting, I think it's 2 or 3 or something, and this integral, this is a solution to Klein coordinate equation, massless Klein coordinate equation. So of course from this perspective we can see that if I give you this full algebra, which is like which is completely spread out at all, which has support on all of scry plus, I can obviously distinguish any states because any state in the bulk, because all states are created by bulk operators which are now isomorphic to this operator. Is the statement clear? This is simply HKLL in flat space. Okay, so this is a trivial statement that if I give you full boundary algebra and I have global hyperbolicity, then of course that algebra is complete and any two states in the bulk can be distinguished by at least some elements of this algebra. But now I come to the main result where why things are drastically different in quantum gravity, which is the following. That things are infinitely better as one is which on gravitational fluctuation, which basically says that consider any epsilon greater than 0, and now consider an algebra which is in some sense the smallest possible non-trivial algebra that you could construct out of this algebra. So let me just define it. We just call it. Let me just call it. Okay, sorry. Let me call it a epsilon boundary, which is a boundary minus infinity to minus 1 by epsilon union scry plus minus. So just to draw a picture, maybe that will be maybe useful. That take any tiny epsilon and take so take 1 by epsilon minus 1 by epsilon, which is as close as you can to minus infinity, but it is a finite number. So it can be arbitrarily large but finite negative number. And look at the sub algebra. It's like how we do the how we look at germ of analytic function, right? In that sense. So you look at algebra which is contained in this for any epsilon greater than 0. So it's a very, it's clearly strictly extremely small sub-algebra of the full algebra, even if this interval is semi-infinite, because clearly epsilon could be as small as you want. So now the statement is that if G is not 0, so I will just write the statement in a minute, but the main point is that if gravitational constant is not 0, then this algebra is enough to classify any two states in the bulk. So we can always find some element A in this algebra, which is such that given any two states in the Hilbert space of the theory, we can always find some element in the algebra such that it will be able to classify these two states. And this is the central premise of why information is not localized in quantum gravity in this sense. It's localized in some sense on a single time slice on the boundary.
Is this the same statement that the algebra with on the epsilon strip is isomorphic to the algebra on the full slice plus, or is it different statement?
Yeah, exactly. And it's isomorphic because the Hamiltonian is a purely boundary term. That's the statement, yes. So he has stolen my punchline. He's saying that in quantum gravity, the algebra on full scribe plus is isomorphic to any subalgebra because the Hamiltonian is a pure boundary term, and that is why this is the result that is coming, right? So if your gravity is not dynamical, then of course this will not be true because you could have stuff which is leaking outside, which is not contained in this algebra. And so if you have a bulk Hamiltonian, then this will not be true. So he's made it more precise. The reason is that if G is 0, then A epsilon boundary is always a subalgebra of A scribe plus union scribe plus minus. But as soon as G is not equal to 0, as soon as gravitational constraints are turned on even perturbatively, we can show that this is same. Okay, I'll just quickly give you in 2 minutes like a quick proof, but I will give reference where you can find this, find why this statement is true.
Can I ask something?
Yeah.
Is there any restrictions on how these functions behave as functions of U so that you can get this result?
Which functions?
The ones in the algebra, C, A, B, M.
Yeah. So no, there is no restriction as such in the sense, of course, we are assuming some reasonable fall-off conditions at large U for matter fields, like they should not grow as log U or something. They should not be divergent. But other than that, there is no condition.
But what if they become 0 before that cut? Would you still be able to distinguish?
But that wouldn't happen in the gravitational theory because of the fact that the Hamiltonian is a pure boundary term. So you would see that by Heisenberg evolution, you will always be able to map operator at some future U to any U arbitrarily close to.
Okay.
Yeah, in the quantum theory, all these operators in the Heisenberg sense will always be evolved by the boundary Hamiltonian, right? So they will never suddenly become 0. Is that what you are asking? So I had a full algebra, which was like I smear it in any which way with some reasonable functions over U. I'm just now taking a very tiny thing where the smearing functions are supported only in this semi-infinite interval, and plus the boundary modes, which include most importantly the ADM energy. And so that's all. So really, in terms of the sub functions, initially, I mean, it's a very, very good point. Sorry, I'm not able to do justice to this question. It's actually a nice question. So in terms of the function that we smear with, usually we'll take functions of, functions which are decaying at large U. Now we are simply saying take the smaller subset of functions which are just 0 outside -1 by epsilon. So that algebra and the boundary modes, that's my algebra. Okay, so now let me just quickly tell you why this thing works in maybe 1 minute.
But those smearing functions.
But this is
those smearing functions don't have compact support, right?
Yeah, this one don't have, by definition. Yeah. So begin with our algebra did not have compact support because it was algebra of because it is algebra on the full scribe plus. Because without gravity, if I want to construct a bulk scalar like HKLL construction, we cannot just use CFT operators with compact support. Because the more deeper you go in the bulk, more you have to smear on the boundary of the CFT. So to begin with, we turned on gravity, we needed this full algebra anyway. Now we are saying that we are looking at a sub-algebra of this algebra. But you are right, it's not. We cannot just look at algebra at around U equal to 0. That will not work because that will exclude the boundary Hamiltonian anyway, right? The ADM Hamiltonian. Okay, let me just quickly give you the result, which I'm going to drop all the subtleties because in flat space we have many vacua. We have not one vacuum. We have so many soft vacua. But in our paper you can find a more detailed analysis. But basic idea is the following: that you consider any operator. Let's say that you have let's take we know that take any operator in the bulk which is of the following type. So let's take an operator X which is of the form summation A n m n m. N and m are some boundary energy eigenstates, and it's some generic operator which I am defining in the bulk. Depending on the coefficients, it could be localized somewhere. Now the point is that we want to ask if this operator, how is this operator, how is this generic operator localized only in terms of this boundary algebra. And the reason it's localized only in terms of the boundary algebra is simply because of the fact that this operator can be written as some xn, which is an operator in the bulk acting on the vacuum, and some other operator acting on the bulk. Now, this operator is like our phi x. I'm just giving an analogy quickly. This operator is like our phi x, which by HKLL, we could always rewrite it in terms of full boundary algebra. So this operator, we could rewrite in terms of, for simplicity, let's assume it's a finite energy operator. So no contribution at scribe plus or scribe plus minus. So this is the operator which is inside a boundary scribe plus. Similarly, this operator is also in a boundary, in the full a boundary scribe plus. It's not supported in a small interval. And this is a projector on the vacuum. But because of what he said, because of the fact that in gravity Hamiltonian is a pure boundary term, any xn, so suppose my xn was an operator which was such that, just very schematically, suppose my xn was an operator, some operator which was such that on the boundary it was supported in this region, if I did an HKLL construction. Then the fact that the Hamiltonian is a pure boundary term, I could use Heisenberg evolution to map this operator back and map it into some very complicated operator in the algebra epsilon.
So yeah, look, we don't need Hamiltonian being a boundary term for that, right? This is just Riech-Leader.
This is Riech-Leader. Sorry. Oh, thank you.
Xn gives you omega is just Riech-Leader. We don't need this.
Okay. Thank you. So this is by Riech-Leader. Yes. Theorem. I'm happy Suvrat is here. So the main point is that where we will. So if this projector was also an element of the boundary algebra, then we are done. And the reason this projector is a boundary element of the boundary Hamiltonian is simply the easiest way to see it is the following. Consider the operator. I think this is in one of Suvrat's papers. Consider the following formally for this operator. So take the Bondi mass aspect, integrate over sphere, and look at this particular operator. And take z going to infinity, so then obviously this gives us the projector on the vacuum, right? Because this is the Hamiltonian. This is the Hamiltonian of the theory. So this gives us omega. And so you see that because this operator is the element of the boundary algebra, which is only true in gravity, this is also an element of the boundary algebra. A epsilon union.
Can I have a question?
Just 1 second, I will just finish and so this is telling us that thanks to Riech-Leader and the fact that the gravitational constraints, any operator can be which any bulk operator which would, so given any two states in the bulk, we could always find one x which will classify them, distinguish them, right? Given any two states psi1 and psi2, always find x. But any x can be written in terms of the boundary algebra, and for the massless fields at least. And so that gives us the this. Now Ashok's question could come that this X is clearly only built out of massless operators. So in principle, if you have states which could only be distinguished by massive fields, then this approach will not work, and we will have to do harder analysis. So that's the proof I've given right now. That's the limitation of this. But at least at this level, it tells us that information can never be, even if I could create these states out of some relational observables, the information is never localized in gravity because of this analysis. So irrespective of how we could create this bulk X, it could be gauge invariant, fully local. We could always map it into a boundary this A epsilon algebra. And if you are not very convinced by this argument, you can look at Kiriakos' paper in ADS-TFT, where they really start with a counter example in some sense, that they really try to define these complicated local observables, which in perturbation theory do commute with the boundary Hamiltonian, but they show that it's inevitable that non-perturbatively G Newton, they will not commute. And so information cannot be localized in quantum gravity. So maybe
so
one
question. Thing to say about Ashok's?
So go on.
I'm done. Even in the presence of massive fields, I think one will still have the full algebra on scribe plus gets squeezed down to this epsilon interval. near scribe plus minus. So regardless of whether so if you have massive fields, that's not the full algebra because you also have the algebra on I plus. But you still have the property that the full algebra on scribe plus can be squeezed down to scribe plus minus. So it's still different from quantum field theory.
Yeah, and that is true. Certainly, that is true. That is true. Yeah. There was a two. Yeah, I'm done. By the way, I'm done.
Is working with this infinite powers of Hamiltonian and okay thing to do like in this projector?
Yeah, this I don't really think it's a problem because this is positive definite and we are talking like the minus z. So I don't see this being problem. No.
Actually, you're still like taking infinite powers and adding up, right? Like it's okay. You say okay, fine.
No, but we don't think of this as infinite powers and adding up, right? It's an operator in its own right, which is convergent, no? In the large z. Yeah.
Like if you have some highly excited state like Kyriakos said, like in what step of this logic will fail? Like,
say the last line again.
Like in this Kyriakos setup, like you are saying there's some excited state, so we will not show holography.
In the
Kyriakos setup.
In the Kyriakos setup.
Like, which step will fail like in this logical setup?
No. Which step is failing is the following. Yes. So Kyriakos will give us a relational observable localized in the bulk. It's a CFT operator, by the way, for them because they have to use ADS CFT, and it's defined with respect to a background state which is very time dependent geometry in ADS. And now we look at it with any boundary charge, for example, let's say boundary Hamiltonian. Then you can show that to any order in 1 by n, it's 0, plus you get a correction of order e to the minus. So it fails non-perturbatively. So this is what they prove. That even relational observables will respect holography of information non-perturbatively.
So you're saying this left side, this is non-perturbative.
Our thing was fully, it didn't refer to perturbation theory at all, right? This argument doesn't refer to perturbation theory at all. But this one is if you say that, okay, let me try to do things more in perturbation theory. Now, there are two things that if you are, as Suvrat mentioned earlier, if your ADS is if the state, so you need a reference state which defines a reference coordinate system. If the state is not crazily time dependent, like say perturbation around ADS, their constructions do not work because then there is no good coordinate. Your state is homogeneous, say for example, it doesn't give you a good coordinate system. So you want a state to be very high energy and very fluctuating. And so for those states, you can define these observables which are perturbatively localized, but not non-perturbative. Is that what you are asking? Or,
like there is no like what is n here in this picture? You are writing some 1 by n here.
G Newton. Yeah. Oh, 1 by G Newton. Sorry.
The spectral density about the state.
Spectral density about the
state, about the excited state that you have. There's a spectral density which is S, the entropy, and I suspect that commutator is actually S. And that indeed for a state which is heavy, might be, will scale with that. Not S by G, I think just S.
Just S.
Just the spectral density, I think.
Okay.
About
Yeah, okay.
I mean, you can make S equal to 1 by G. Just if you take a heavy state, which is,
I understand.
S will start scaling with it.
Yeah, there was question. Spenta has a question.
Yeah, I just, can you briefly indicate if you have massive particles?
Suvrat and I think the point is that if you want to do holography, I mean, as we discussed that, most natural home for massive fields is I plus or I minus. Yes. But somehow I plus I minus is not, for several reasons, it's not very good to do holography in the following sense that first of all, you can be very close to the center. So you're spatially not far separated. Plus the structure of I plus I minus is not very well understood if you have black holes. Like, we understand how to define them, compactification here, if you have asymptotically flat geometry, but no like black holes. In black hole, there is still no complete understanding of how to define I plus. So in that sense, probably the best place to define observable for massive field will be the spatial infinity. So, the idea that if you could define algebra of operators for massive fields at spatial infinity, then it will be very interesting because we could in principle say that, look, I have a region which is at large spatial distance from the center where I'm able to define my entire algebra of observables. And first step would be to do something like HKLL for massive fields without gravity being turned on. And so here Suvrat and his collaborators, they have done some work about looking at say interacting massive fields and how you can really project them onto spatial infinity, this hyperboloid. And actually they get some quite interesting observables like what I would call square root of S matrix in terms of correlation functions of these things. So I think Suvrat can correct, I think gravity is still not included, but the hope is that one would be able to define the full algebra like in ADS on this, some kind of a boundary which is localized around spatial infinity. So spatial infinity plus an infinitesimally small neighborhood at Scri plus. That's the hope at least, yeah. Sandip, so I have to, sorry, just 1 minute, Sandip. So you have to give me 2 minutes to write references, but yeah. Okay. Yeah. I will take 2-3 minutes to write them. So Ashok has a question.
Questions. One is that how dimension dependent is this analysis?
I think it is, in my personal opinion, this is dimension dependent because of the infrared effects. So we would have to worry if you, as we discussed that for massive fields, for massive fields, if you go to large, say you are at I plus, then they are not free at all, even classically. And so then this analysis would really depend on because we are doing things in infrared, right? So if you have infrared divergence, then we will have to worry severely about infrared divergences. For example, if I want to say what kind of observables in the bulk I want to capture at the boundary, then naively we would say, okay, then most natural observable in quantum gravity is S matrix. But S matrix is infrared divergent, so we would have to first understand how to define S matrix to actually see what it's related to in the boundary, right?
But even in higher dimension, even though the S matrix is finite, there is still the vacuum is still degenerate, right? Because there are infinite number of the massless modes are there.
Yeah.
Right. So in this projector that we define, right?
Yeah.
It doesn't cause any problem. That fact that there are
so we haven't looked
arbitrarily light states.
Well, so maybe I misunderstood. So even in 4D, there's an infinite degeneracy, as you know, of this thing.
Yeah,
and
exactly.
we can sufficiently distill them using the boundary algebra. I just didn't go into that detail.
Okay.
So
but in higher dimension, for example, right?
Yeah, I don't know, Suvrat may know, I haven't really looked at this. Because higher dimension, just before Suvrat says something, let me just also mention that in odd dimension, we have other issues. Because the fields follow fractionally. To define the boundary algebra, there are maybe some analytic subtleties that we haven't completely dealt with. But maybe Suvrat, you want to say something about?
No, in 4 dimensions, as Ashok is saying, that actually this projector in the vacuum is not I mean, we have to project onto super translation eigenstates and
No, but Ashok's question is without super translations, right? Just arbitrary low energy states. And so what was the issue, Ashok? Sorry.
I think we want to use some basis. This projector we can define in some normalizable basis for the Hilbert space, right? So we take some basis for the Hilbert space. This projector is causing confusion because we are taking a basis where we are taking states which we are taking some momentum basis. But in fact, that momentum base is a little deceptive because it's not actually carrying information. So you can look at the Hilbert space in a slightly different basis. And, where the states are normalizable states. If you do that, then, you'll clearly get a projector on the vacuum, right? The fact that you have very low energy modes, that's true, but it also carries very little information in that, two states which are distinguished just by some very soft photons, are basically, not very distinct. So I don't know if I'm being clear, but.
And sorry, can we, since we have only less.
I just take 1 minute to write some reference, then we can just end.
But let's thank Alok.
Thank you.
Aren't you going to write up some notes and, this is a school, so aren't you?
Okay, I will try to.
I think you should do it. I think it's a good thing to do.
Okay. I will.
You're addressing students all the time, no?
Yes, absolutely. Yeah. I totally agree. Yeah.
It'll be good for me also.
So this is the paper by Philip and his friends on relational observable, which I extremely strongly recommend. And then there are I would say the program of holography of information is really pioneered by Suvrat and his friends. And I'll just write some of these papers, but you can find many other references. Oh, by the way, I should say that this, I think, let me just write this. These two are ADS papers, and this is flat This is incomplete list, by the way, because Suvrat has many other papers in this. But one paper that I especially like is with Chandramani and Olga, and that I think this is a very beautiful paper, which is this one, where they really show how they solve perturbatively Wheeler-DeWitt equation and show how perturbatively holography of information, at least for simple states, not Kyriakos type states, can really emerge. So this is a very beautiful paper because it doesn't rely on any formal arguments and does a rigorous perturbative analysis of Wheeler-DeWitt equation. And actually, the precursor to this holography of information by Suvrat was really older papers of Marolf. At least the ideas were sketched in this paper, like this paper, which really, as far as I know, is the first one which kind of says that single time slice boundary algebra is enough to capture the full algebra. And now the thing that I did not cover, which is the de Sitter quantum gravity. So I just give some references. There is a paper by a very nice paper by Sandip and Kanu and Sunil in two-dimensional JT gravity with positive cosmological constant, where they discuss the issue of observable dynamics in quantum gravity. This is 2D. And then papers by these are two papers by Suvrat and collaborators, Suvrat, Tunir, Priyadarshi and Joydeep and Victor, both these papers, which are closer in spirit to what we discussed about this holography of information. So this is by, I will just write the name, sorry. Then okay, and finally I should say that in many ways, in many people in 80s in obscurity thought about many of these problems, and so we should pay some homage to them, and especially Karel Kukash, who kind of stuck with these issues for a long time in 70s and 80s, and he has a very nice review on observables in quantum gravity. I think it's still very this one, and then this this Brown and Kukash dust model paper, which is this. This is the Brown Kukash. Okay, this is a heavily incomplete list, of course, and this is a very beautiful review on problem of what was called problem of time in quantum gravity. So, this one.
Which one? Oh, I see.
Yeah, the very first one.
Okay.
Yeah. Sorry? Yeah, it's 19304012. Oh, 012. Yes.
Okay, yeah, let's thank Alok once again.
Yeah, sorry for going over time.